So, as I say, welcome to the ZP Developer Zone. We like to do this webinar every Thursday, 8 a.m. London time. And as I say, I will try and jump straight into it. So the first thing is, I put this slide up every week, and I will be very quick about it. I don't want to, I don't want to waste people's time on this, but we have the ZP Academy that is relevant this week. There's a couple of free courses on it, and I'll just mention it very quickly. So we have the ZP Academy. We do have the webinars every week. So the intention of these webinars is people have technical questions. If the questions are relevant and more sort of generally interesting to the to our community, then we talk about that. We do have our collaborations. Now collaborations really do generally mean sort of collaborations with university partners, academics, for example. We do post jobs, and I do feel now that despite a global turn down, actually it's not a global turn down in the sensor market. So I wish everyone good health in this sort of global stress time at the moment. It's not quite the same in the sensor industry, because we're also partly in healthcare as well. And we also have our ZP Developer Zone website. I'll go a bit quicker as well, I think, because I'm sort of conscious of the time. Now we also do have workshops as well, so I will discuss that. So one of the workshops that ZP is holding at the moment, or is holding next week, is on the 14th and 15th of September in Horten, so obviously in Norway. Well, not obviously, but it is in Norway, and we'll be holding a workshop on CGM, continuous glucose monitoring, and we will be covering other sensors like lactate and oxygen, etc. in that workshop. It's also worth knowing that we are having a workshop organized by our partners in India, by Technando, and we will be having a workshop around IIT and SSN. So 2 workshops, 2 days, a gap in between them. Now the ZP Academy is useful because today's topic, we're not really going to talk about electrochemistry too much, but I do want you to know rather that there are a couple of free courses on the ZP Academy about electrochemistry. One on introduction to biosensors, and one on electrochemical techniques for biosensor developers. Now today's topic is around the detection of organic solvents and organic liquids. So I will sort of jump into it, and it's a little bit like this. The scenario is that you have probably a vapor, and it could be a vapor of sort of organic materials. This could be kind of kerosene or gasoline or petroleum. It could be an organic solvent, toluene, dimethylformamide, dichloromethane, for example. But it's here I'm representing this vapor by these sort of green dots, but we have a vapor. Now the idea is, how can we detect when this vapor has condensed in an absorbent? So the vapor is otherwise in the vapor phase, but when it reaches an absorbent, the absorbent essentially brings the droplets together enough, and we get a sort of coalescence of those droplets, and then can we detect it? So the scenario I'm describing then is you have an organic vapor. I mean, often, at high enough volumes, you can obviously smell these kind of things, but we're trying to determine how can we detect it. So you have the vapor. It's otherwise being carried in this kind of vapor / gas phase. When it reaches an absorbent, these absorbents essentially could be like sponges, and you get a coalescence of droplets, and you actually get a continuous liquid phase. Now, there's 2 parts to this. There's the science and there's the engineering. I'd actually say the engineering part was simpler. So what I mean by the engineering part being simpler is this. At Zimmer and Peacock, we do have a mesh network solution. So it means that we can have, I'm showing we call it a sensor rod here, but we have telemetry in the head and the electronics, and then the red squares represent a couple of sensors. So the engineering is actually quite straightforward. The science is something else on this one. But first of all, the engineering is simple enough that you can have a couple of sensors. connected to a telemetry head. The telemetry head can send to a base station, and the base station then, if it's on the wireless, we can send the data to Julie. Julie is a cloud system. I'm personally using Julie a lot these days. So Julie is something that we've developed at Zimmer Peacock, and it can receive basically data. Now, through data then, and this is what we're doing at the moment, we're processing that data into information. So I have a program on at the moment I'm involved with where the raw data, in that case, it's amperometry. And if you don't know what amperometry is, it's fine. Just have a look on the ZP Academy. But anyway, it's a project that I'm working on. We're sending the amperometric data to the cloud, but then we're processing it through, I want to say sort of templates. But what they're doing is then turning the data into information. So we're turning the data into information, and then we're able to send that to people's, for example, in our nitrate program, we've end up sending it to the smartphone. Or we can also do what's called API, Application Program Interface, where somebody else can call upon it in their cloud. So if you're an engineering firm, you might have a sensing application. It could be in a kind of warehouse or something, and you want to give a very specific user experience. Therefore, you would have your own cloud, your own dashboard, and you would bring data across using an API, an application programming interface. So we're able to then actually have multiple sensors in a let's say an environmental application where each sensor rod is able to talk to the other one, and we're able to sort of daisy chain over some distances. And we can also have repeater stations, and it works with a lot of our sensors. Now, the reason I've said all this is, let's go back to the original question. The original question is, I wanted to be able to detect a condensate of organic material that's condensed into a sort of mesh, and I want to be able to detect it's there. The engineering side is fine. If we can get a signal, sending it across a network and sending it up to the cloud, completely fine. That's all done. And for example, one of the applications of that mesh network looks like this. This is something that we did for continuously measuring nitrate in soil. I will move on a little bit faster now. My problem is the science of this. So today, I'm not going to talk so much on the techniques that we use at Zimmer Peacock, but we do use voltammetry quite a lot. We do use impedance spectroscopy quite a lot. We do use potentiometry quite a lot. I'm not going to talk about those techniques because they are in the ZP Academy. I'm trying to stay sort of close to the spirit of the question. But if you are interested in electrochemical techniques, please try out the ZP Academy. So if I was doing this work, if I was doing essentially a proof of principle in the lab, then I would take one of our screen printed electrodes. I would run it in air. This sounds ridiculous, but in some ways, the detection of liquids is straightforward. Detection of liquids is straightforward. The specific detection of a specific liquid, that's a different question. But if I was trying to do the detection of liquids, that's actually quite straightforward. You can detect liquids using there's lots of engineering solutions out there that use conductivity or use capacitance. So the detection of liquid, I have no issues with that. So we would take one of our electrodes and run it in air, and we would get a very, excuse my coughing, we get a very low signal, almost 1 or not less nanoamps, and it's almost just a leakage current. So I would take one of our electrodes. I would do something like voltammetry. Voltammetry is not necessarily the best, but it's just a starting point. And I'd get a very low current and something pretty close to zero. Now, I would then add an organic solvent onto it. And the organic solvent, even though it's organic and quite, let's say, resistive, it's not conductive, I would get a new type of signal. It would be a very capacitive looking signal. It's a silly phrase, but it means something. It sort of means that I can for me, and I would get a signal for it. Now, the problem that I have with this question is, I can use lots of electronic ways of detecting whether a liquid has arrived. So I don't feel like I'm adding a lot of value to that. Yeah, a liquid's arrived. We can find that quite readily, and I can prove that in the lab. I could almost prove that in the lab, in our lab, within sort of 5 to 30 minutes, really no issue. Just go to the solvent cabinet, take out some solvents, drop them on the sensor, get the signal. That's not a big issue. Now at Zimmer and Peacock, we try to help people not only detect something is there, but we also try to help them with the sort of specificity. What is it, for example? So the question is, in these kind of applications, is it enough to just detect that there's a organic solvent there, or actually do you want speciation? So when we have a molecule like the one on the left hand side here, we have a lot of functional groups, and we can get a I want to call it a spectrum. It is a voltammogram, but people always, the term voltammogram kind of worries some scientists, and one day you just realize it's equivalent to a spectrum, which is a sort of term more commonly used in sort of photospectroscopy techniques. But a molecule like this will give us a very distinct spectrum / voltammogram, and these peaks will tell me, give me a fingerprint and say that's the right molecule. Now, when you looked at my previous slide, I didn't show anything with these kind of peaks and troughs, because the molecules that are being requested in this particular, let's say, inquiry are very, they don't have a lot of functional groups that are necessarily addressable by electrochemistry. So I'll dig into that a little bit more now. So the molecules of interest are things like butane, tetradecane, DCM or dichloromethane. I don't know why I put toluene in there. I don't know if sure toluene was there, but anyway, toluene I've put here. I've also put DMF, dimethylformamide. A lot of these molecules, in some ways, there are some interesting things like this carbon-chlorine bond. I've noted that, and the DMF does have oxygen and nitrogen, so these are some handles. But these molecules don't give us necessarily very distinctive signals. So we can get a detection signal from it. It's basically asking the difference between air and liquid. That we can do. But specificity, like I showed on the previous slide, where you get these very distinct peaks, that I am not promising by electrochemistry. I'm just not. Maybe, this is unusual, and this is the way Zimmer and Peacock thinks. We are essentially a sensors and consultancy. It might be better to go with the infrared spectrum solution. Now that's unusual coming from somebody with a PhD in electrochemistry, but infrared actually may be the better course of it. So I've put the infrared spectrum for DCM because the carbon chlorine bond can have a sort of distinctive spectrum. So that would allow you then to basically detect that there's a liquid there, and promises and doing, that takes investment, but it would give you a spectrum. The same for DMF as well. It also has its fairly good spectrum. My concerns are this, that if somebody asks me, can you make a low cost electrochemical network for the detection of liquid? Yes, I can. We've been doing that for many years. With infrared, I'm a little bit worried about the cost and robustness, so that would have to take a bit more work before I would, put a reputation behind that. But if I was to back up a little bit, the question is, can you detect organic solvents? Yes, we can detect organic solvents. It's quite straightforward. You could probably use it off-the-shelf sensors today that relied on either conductivity or capacitance. You would have to look into their compatibility with organic solvents, but it can be done, and ZP could do it as well. And I think a proof of principle in the lab really wouldn't take that long. That's detection. That's not being specific and telling you what it is. If you want to be specific, I think actually electrochemistry would actually struggle quite a bit with the specificity part. And I might actually be suggesting, if you want specificity, then you might have to think of a new, different technique, and infrared spectroscopy for somebody who has first degrees in chemistry would seem like a good place to actually go looking. I would be worried about cost and robustness. That needs to be looked at properly. And my other concern would also be background. If you're trying to do specificity, in a lot of environments, the background signal or the background molecule is often water, water vapor. And that has a very I want to say intense signal, in fact. Now, it's different from those organic solvents, but the broadness of these peaks could end up masking things a lot. So I've said a lot there, but I'm kind of saying organic solvents, their presence can be detected. The specificity is a little bit tougher. Infrared possibly has greater specificity, but in an industrial application or an environmental application, you do have to think about background molecules, and water would be one of the ones I would be concerned about. Now, with the electrochemical route, if I was doing this in a lab, these are biased opinions because we manufacture this, but I would actually be using an ANA EIS, or electrochemical impedance spectroscopy. The reason I bring up impedance spectroscopy is because you would be looking for both the detection of that molecule and you would be trying to get some specificity. Was it dichloromethane or DMF? I would be trying to use techniques like EIS, electrochemical impedance spectroscopy, to help me answer that question. So if I was going to be doing research around it, I'd actually be using a much more high-end instrument to help me, because then I could play with EIS, I can play with square wave voltammetry, differential pulse voltammetry, cycler voltammetry. It gives me more tools to play with in my, let's say, research phase. Whatever came out of that, I could then translate it onto the mesh network. But you need quite a high-end instrument. You can't do this on a sort of low-cost instrument because it doesn't have enough options. If the first option doesn't work on a low-cost instrument, there's nothing else on the menu, you kind of wasted your time. So you have to get in my opinion, and we have lots of these instruments ourselves. You need a cable. I'm being very specific here. This is the cable that I would use for this particular instrument. You need a connector, and this is the connector I would use with this instrument. It's chosen specifically because it works with the cable that on the previous one, and it will also take one of our 10mm SPEs, screen printed electrodes. All these links, by the way, I've put them underneath the YouTube video as well, so people can really help. There we are. See, and I've just got an answer coming through now as well. The Inquirer has actually looked at IR, and that's my concern then. So IR equipment is costly and bulky, and that really is the comment that I just made. That was my, cost and robustness. So the question comes down to this: if it's enough to detect that you've got a condensed phase, electrochemistry is completely fine for you. If you want to do speciation, and therefore by speciation, and by the way, if you want to determine whether it was tetradecane versus not ibutenes, that's probably in the gaseous phase anyway. But if you want to detect the difference between these different molecules, I think the electrochemistry is actually, unfortunately, not a good technique for it. You can detect that they are there, and you would be able to potentially detect the difference between a liquid phase that was water and a liquid phase that was organic solvent. Essentially, as you could intuitively know, water is obviously a dipole molecule. It can act like a sort of conductor, whereas a lot of these organic molecules can act much more like insulators. So what am I saying here then? That I've suggested infrared spectroscopy. The Inquirer has actually said no, it's too expensive and it's too bulky. Right, okay, so that might mean you might have to fall onto an electrochemical technique. And what I'm saying about these electrochemical techniques is, I'm just going to read, I'll just read the question in a minute. The problem with these electrochemical techniques is they'll tell you that you've got a liquid phase, and you could probably distinguish them between whether it was an aqueous or water-based or organic. We can get to that point. So the question that has come through is actually how far can the instrument be from the electrodes? It's a tricky question, but I want to be a little bit careful on this. If it was a potentiometer, so the quick answer is I imagine that 1 or 2 meters is fine. I might change. I'm not going to say direction in a minute, but I might show some instruments as well on this. But we've talked about infrared spectroscopy. It's been dismissed. If I was to do this, I would be using quite a high lab instrument, the connector, and I would be using one of these screen printed electrodes. Now the question is how far can this screen printed electrode be from the instrument? If I was to put my, it's taking a slight risk. I wouldn't have a problem with 1 or 2 meters. The reason I'm sort of slightly nervous on that is because, obviously, wires can essentially, everyone knows this. Wires can act as antennae, so you have to really, think about the shielding and the grounding of wires. So the answer is slightly nuanced. That electrochemistry is not a bad technique for having a sensor remote from the instrument. Obviously, it then becomes a little bit environmentally sensitive. You're in a high electromagnetic rate, an environment with a lot of sort of electrical noise in it. How well have you shielded the cables? So it does really become like an engineering thing. But there's not an intrinsic reason why you can't have some distance between them. But, it can be a nuanced answer. It really means you have to sort of try, and you have to put some engineering into the sort of shielding of your wires. We do have the kind of electrodes that would do this. So we do, and we do have some notes out there about the resistance of the of the screen printed electrodes to organic solvents. I'm sure the inquirers found that. So these electrodes are actually quite robust. And could they exist sometime in an absorbent material? Yes. And my biggest concern is that specificity, that they'll detect that there's something there, and you can even get to the point, I've said it already, that actually whether it's aqueous or organic, I think we could get to that point. But then, if it was different types of organic solvents like toluene versus tetradecane, that I would struggle to say a little bit. I'm just going to talk about instruments really quickly, because what I want to say is this is with the nice thing about electrochemistry and unlike any sort of photo systems, is this is one of the instruments that we've built. So this is the sensor here. These are just the wires to essentially bring in the signal into the package. This is the electronics. A couple of coin batteries here. This is an unusual application that we're actually transmitting data through water. So it's actually a piezo transducer. We're actually beep, beep, beep. It's literally how we're sending the signal. A bit crazy, but it's salt water, so we have to do it that way. Now, the question there is really asking how far can the sensor be from the electronics? And I would say it's actually a bit unusual in electrochemistry that the electronics, this is probably one of our smallest boards. It's 7 millimeters, obviously in that dimension. These 2 bits snap off. They're just really for sort of handling and programming. So you can have a package in electrochemistry where the sensor and the electronics are actually quite, close to one another because it's intrinsically small. I mean, if you told me that you were trying to make, there was a dry wall and you were trying to know whether a solvent was impregnating into that dry wall, it wouldn't be, you could have a package that's actually quite small, and this is, we'd have to put Bluetooth on it, but then send the data out by Bluetooth. So, for example, the quick answer is, I think you can have electrochemical sensors at some distance from an instrument, and, I'm not taking too much risk by saying 1 or 2 meters, but you have to shield the cables, you have to twist cables, you have to make sure that you've sort of reduced that electrical noise capability. It's also worth knowing that if you are looking for a low, in the end, it has to just be low cost and low form factor. I actually generally think that if that's the driver, it is electrochemistry, because the instruments are just so intrinsically small, let's say, these days. In fact, I mean, on our website, we do have technologies that we kind of call glucose to API or pH to API. So I'll try and find one of those very quickly. In fact, this is actually, I just happen to have a picture here. In fact, it's not impossible to have electrochemical sensors or electrochemical electronics are small like this, where, in fact, this is the Android phone, this is the USB-C connector, that is the electronics there, and I'm sorry about the smallness of the size of this, and that's the sensor itself. So I'm going to roll back a little bit at the moment and say this, right? people might be interested in detecting the presence of organic solvents. If IR is not going to work for you, then I would suggest that actually electrochemistry is good, because in fact you've already looked at IR. The reason I was looking at IR is because actually I think it will give you specificity, but that was my concern, that actually they are bulky and they are expensive, and I was a bit worried about the robustness. So if cost and robustness is more important to you, then electrochemistry does become the sort of technique of choice. You know, why are most glucose sensors on the market electrochemical? Because in the end they wanted them to be small, low cost, you know, to manufacture devices, and then electrochemistry just starts winning out a bit. I'm just going to read a question. Yeah, good. So so Bluetooth. I mean, having packages. I'm just going to look up something called CGM Developers Kit. So Zimmer and Peacock putting together what I would call MVPs, minimally viable products, around the idea that this is something that we have on our website. So what we have here is a little essentially box. In that box is a potentiostat. Into it we can plug the electrode, and in there's actually a Bluetooth, and I think it's both Bluetooth and it can do Wi-Fi module. So we have a sort of Bluetooth, and I think it could do Wi-Fi. So that kind of box factor, and there's the sensor there to give you a sense. That would be an okay to produce, you know, that something that you could produce for detecting organic solvents. This one is actually enabled then that we can send our data straight to our cloud. So if you're interested in small form factor and Bluetooth, then it's probably worth looking at our wearables platform. I'm going to slightly back off now and say, and we do have the right electrodes. It will be resistant to organic solvents, etc. So I was expecting this to be quite a short webinar. My concern is that actually, you know, this is in some ways the science, you know, when I'm sort of speculating like this, I'm a bit worried that the science is at the moment is in its very infancy, so I don't want to overpromise on that. The engineering is probably a lot higher actually. You know, if the science works, the engineering is actually ahead of the science, but the science has to be done. So I'm going to slightly apologize now and sort of do a summary. Right, so today we've been doing a slightly unusual one, the detection of organic liquids, organic solvents. Their detection is fine. The specificity I struggle with a little bit. But in some broadness, I think you can definitely tell the difference between a organic phase, or organic liquid rather, and a aqueous liquid, because they have very different conductivities. If you want to call it dielectric constants. Yeah, that's great. So if you want to detect, then electrochemistry possibly is your guy. Infrared, I'm enough of a chemist to say, you know, there are alternative ways. I did have a slight concern that it sounds like it's the panacea, but it can be quite robust. The reason optical systems are often quite big and quite power hungry is because it's harder to count photons than it is to count electrons. This is almost just the fundamentals of it. An electron has mass and it has charge, and we can quite simply detect it as a flow of current. So no concerns there. But photons, actually, they have no mass, no charge. They can be quite expensive. I'm just reading the question here. Yeah, cool. Right, so I think in a QC type application, which, you know, quality control application, QC applications are actually quite good, because in a quality control application, the system is meant to be repeatable. So if you have a quality control tool which says, is there or is there not organic solvent present in this product or in this process, that is quite a repeatable process. So that everything's defined. When you try to put like a sensor into an environment where there could be lots of parameters that could influence, that's a very different thing. But if it's a QC application, those are often actually, you know, more about repeatability, and therefore you can tune the system to the QC applications. And yes, we do have a a screen printed electrode to do that. So small packages are fine. Electrochemistry can be low cost. You can have sensors remote from the electronics. I'm not even sure that you need it because the electronics are actually quite small. So I do have to just check the time. Yeah, 8:30. So I apologize. Like everyone else, I do have meetings to go to now. But at Zimmer and Peacock, we do these webinars once a week. If we get an interesting question in and we think that it's not always easy to answer these kind of questions. You know, you can see that a lot of thought goes into this kind of stuff. Then we bring it to the webinar because it really gives us the forum to really think this kind of stuff through. So I want to thank you for the questions this week. There's an interesting question there about fouling. Yeah, fouling. You can deal with things like fouling by possibly having membranes like PTFE on the top of the electrode, etc. There's always a solution. Well, not always a solution, but there are solutions. All right, so I want to say thank you very much. I will jump to some meetings. Thank you for the question this week. If you're watching this and you have technical questions around sensing, then Zimmer Peacock is willing to help. So thank you very much, and thank you for the question. It is appreciated. All right, take care, guys, and thank you so much for the question.